If you go back the last 10,000 years, you see we're still relatively warm, although it was a little warm, maybe warmer 5,000 years ago. And again, I'll come back to that in a moment. And then there was the last glacial maximum, which was about 15,000 years ago. And then you can go back 100,000 years. This is the last glacial maximum. We were relatively warm, and the last time it was as warm as it is at present was about 100,000 years ago. And then you can go back, again, 1,000,000 years, and one has glacial cycles. I don't want to go into how all this information is derived, but that's one of the great sort of mysteries and searches that exists. I think the thing to notice, though, is that if we increase 2 to 3 degrees, which is what is projected if one doubles CO2, you're going to get to a climatic state that is basically unprecedented in the last perhaps 100,000 years until you're back to here. The climatic optimum, which is this 5 to 7,000 maybe year period here, was maybe 1 or 2 degrees warmer, and there's people who are looking at that as an analog for the CO2 state. But in terms of man's history, being 2 to 3 degrees warmer is sort of going to be an unprecedented event. There's been some tendency to change the term unprecedented to mean bad or catastrophic. That isn't necessarily true. People are starting to try and decide whether it's actually good or bad to be warmer. I mean, if you tell the people in Chicago in the winter that it's going to be 2 degrees warmer, most of them would be delighted. On the other hand, if you look at the changes that have occurred over the last 10,000 years ago, 10,000 years, it turns out that the change in ocean temperatures, this is actually some measures of land temperatures and stuff, but the global average ocean temperature during the last glacial maximum was about 2 degrees cooler than it is at present. So 2 degrees for the global climate is a major kind of change that can occur. Well, let's talk a little about how CO2 affects the climate and how it enters in. Basically, it enters in as a factor in the radiative balance of the atmosphere by trapping radiation, basically long-wave radiation that's emitted from the Earth to space, by trapping it and making it harder to escape to space. So it's, I guess, sort of like adding insulation on the atmosphere. And I don't want to quite say greenhouse because that's not how a greenhouse works, but it's basically like adding some insulation on the top of a house. If one then does a test simulation where you take an atmospheric profile and double the carbon dioxide concentration, as shown on the next view graph, and I apologize here, I'm going to be switching units a little bit on you. The units here, 100 here is the solar radiation input, so this is 70% of the solar radiation. Basically, the Earth's energy balance, 100 units of solar energy come in, 30% is reflected. Long-wave radiation balances the rest. The numbers outside of parentheses are what the normal fluxes are, 70 going to space. Note that the radiation from the surface to the atmosphere is actually larger than the radiation from the sun to the Earth, which is an indication of this trapping of radiation. The net flux from the surface, however, is pretty small. There's a lot of back radiation coming down from the atmosphere. And so one can look at the normal balances of what's happening here. In parentheses are what happens if you double carbon dioxide. And these changes look very small. That is, in the net, you're increasing the trapping in the troposphere by only the equivalent of 1% of the solar constant here, and about 0.5% at the surface. The stratosphere, on the other hand, cools because it basically radiates directly to space for reasons we won't get into. So you're trapping the equivalent of like 1.5% of the amount of solar radiation. That seems kind of small in terms of 100% coming in, and in terms of leading to an unprecedentedly warm climate. And I want to try and explain why that's true without without just relying on theoretical models to do that. I think the first thing to do is to compare the thermal effect of the radiative effect of CO2 with the thermal effect of just burning all the carbon that you have and releasing energy, the thermal energy that you release. So if you look at the change that's going to occur over maybe the next 50 years, we're using 8 times 10 to the 12th watts, and it's going to go up. It's going to go up about a factor of 4 in the next 50 years, according to some people's projections. If you convert this to a watts per square meter kind of use, and I'll be showing on the next slide some stuff about the CO2 effect and that. You see it's a few hundredths of a watts per meter square that you're changing. The next view graph shows, and the last one did show, I didn't do the units conversion on it, but shows that what you're really doing in terms of the radiative effect is getting up to, in the lower atmosphere, trapping more than 3 watts per meter squared, so that the ratio of what's happening, the radiative effect, compared to the thermal effect is like a factor of 80. It's kind of an incredible ratio, but that says something about how CO2 is acting in the atmosphere. And in fact, if you run a model to equilibrium, including the various feedbacks that occur, and we'll get into them, the change in downward flux at the surface is about 12 watts per meter squared. So compared to the 400ths of a watt per meter squared that you get from the thermal emissions of it, you just don't have to worry about the thermal emissions compared to the radiative emissions. Well, once one has done the radiative aspects, and as I say, I'll come back some more and try to interpret what the models mean. I want to basically talk about how we approach the problem with models to try and incorporate all the processes. And basically, the models are based on the physical laws of the atmosphere, treating the land and the oceans and the atmosphere, sea ice if you have to, and things. And they treat a lot of different processes and causes and effects that are going on. And this is sort of one person's diagram of it. The next one is one person's diagram of all these kinds of feedbacks that are going on. This isn't something that we're going to try and understand. It's just to sort of show the confusion that occurs. And this doesn't necessarily include all of the things that are happening. I mean, I've added a few arrows in here. Maybe you can note they're the same color, but a lot of things were not in this original chart. They didn't have temperature affecting the composition of the atmosphere, which is something that clearly happens in the stratosphere, or the water vapor affecting atmospheric composition. There's a lot of processes going on in the atmosphere and a lot of cause-effect linkages. Some of them are really important. The one that's probably most important is the water vapor feedback mechanism, and let me just sort of go through on the next slide how this process works to amplify what's happening. Basically, if you increase carbon dioxide in the atmosphere, you increase solar absorption a little bit, but mainly you increase the trapping of the infrared radiation. So the atmosphere warms, which by radiating to the surface warms the surface, which leads to more evaporation, which is one way the surface gets rid of moisture, which leads to an increase well, this radiative change has led to an increase in the air temperature, and it also leads to an increase in how much water is in the atmosphere. Well, this increased warmth here will lead to, increased water in the atmosphere will lead to more capture of solar radiation, because water absorbs solar radiation, and more trapping of the infrared radiation, because water, like CO2, traps the outgoing radiation. And this process will feed back on itself. And we'll go through that in a few slides about how much that actually occurs. I guess I'll come back to that. The next slide shows that there are quite a number of processes that occur this way. There's water vapor. There's the surface albedo. If you reduce the amount of radiation reflected from the surface so that more is absorbed, so if you reduce the amount of sea ice, more radiation is absorbed in the ocean, so more heat can be transferred to the atmosphere. And that occurs instead of reflecting it to space, so that there's a sea ice albedo, a snow cover albedo. Clouds can certainly change. If there are more clouds, they do two things. One, they reflect more solar radiation. The other thing is they trap more of the long-wave radiation that's coming up from the surface and re-radiate it back down. And there's a lot of controversy about what effect clouds will have in the CO2 problem. Changing the moisture of the soil changes the reflectivity of the surface. And there's some effects on stratospheric chemistry that's sort of entirely another discussion. Well, if one takes a model, and let me just show sort of the classic one. This is the first three-dimensional model result that was done by Manabe and his colleagues at the Geophysical Fluid Dynamics Laboratory at Princeton, for which I happen to have the nicest slide, I think. What happens in the upper atmosphere is with more CO2, and it's so the atmosphere being so thin, it can just sort of radiate more effectively to space, and so the stratosphere cools until it comes into a new radiative balance with the solar radiation absorbed by the ozone. The lower atmosphere sort of warms 2 to 3 degrees at most latitudes, but there's an amplification of the change in polar regions. Some of this is due at least to this ice albedo feedback mechanism, because there's sea ice up there that can change. The other factor is that there's usually a strong polar and temperature inversion up here, and so instead of having to warm the whole atmosphere a lot, it really only has to warm a relatively thin layer of the atmosphere, and it doesn't take as much energy to do that. So with a finite amount of energy, you can warm the lower atmosphere even more.